Hello and welcome to College Algebra, Lesson 6.5 on rational functions and rational equations. There are two main parts to this lesson. One is all about graphing rational functions, looking at their asymptotes, their vertical asymptotes, horizontal asymptotes, and slant asymptotes. The second part of the lesson will be about solving rational equations and solving inverse variation problems. So to get started, we're going to start with graphing. First of all, what is a rational function? A rational function is a function where we have p of x over q of x. This just means there's a polynomial on top and a polynomial on bottom. They can be simple polynomials. A polynomial can just be a number, or it can have x's in it. Q of x can't be 0 because then we would be dividing by 0. The most basic rational function that we're used to looking at is the function 1 over x. And if you recall, when we graph 1 over x, it looks like something like this, where it has a curve up here in the first quadrant and in the third quadrant. So it gets these two pieces with curves. We have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And we'll talk a little more about that, but that's the basic one. And then we're going to change it by changing our polynomials. So here is our first example. Polynomial on top is x plus 1, and on the bottom we have x plus 2 squared. So find the vertical asymptote. Well, where is the vertical asymptote? If you recall from the little 1 over x, it came from the bottom here. We're not allowed to divide by 0, so it is what value would make the bottom 0. So x plus 2 squared, where does that equal 0? Well, we don't really need the squared because we could square root it and we still get 0. So where does x plus 2 equal 0? It equals 0 at x equals negative 2. So that's the vertical asymptote is at x equals negative 2. So if we were to graph this at negative 2, there would be a place where it does not cross. So if we wanted to sketch a graph of it, we could plot a few more points. For example, let's make it like a little table of values here. Well, if I plug in a negative 2, I'm going to get undefined. So NA, there is no answer at negative 2. There's no dot there. I could plug in a negative 1. Let's just go that way and see what happens. So if I plug in a negative 1, I get 0 on top divided by anything, as long as it's not 0, would be 0. So negative 1, 0 is actually a point on my graph. And then let's plug in a 0. If I plug in a 0, I get 1 over, plug in a 0, you get 2 squared, which is 4. So 1/4. So 0, I'm at 1/4. We could keep going and plug in some more points. You could also put it in your calculator. One thing to be really careful of whenever you type these in your calculator is we have to do the whole top divided by the whole bottom. So you have to insert those parentheses there. There already are parentheses on the bottom, but not the top. So I was going to show you what that graph looks like. So if you kept going and plotting points, you need to make sure you do some on the other side of the asymptote as well, so you get both parts of the curve. So this one has two pieces that look like this. All they wanted was the vertical asymptote in a sketch, so we did that. Here's a new problem. Suppose that for specified values of p, the function c of p can be used to model the cost of removing p% of the particulate pollution from the exhaust gases at an industrial site. First of all, we want to graph this. And again, be very careful. Put it in your calculator. You don't have to put them on the top, but I would. Put parentheses around the top, put parentheses around the bottom, and type that in your y equals screen. Now, in order to see this, we're going to have to change our window. It was nice enough to tell us what window to use so that we can see a nice graph. So get that put in your calculator, pause the video, and then take a look. So here we have a picture of that graph. And it hasn't asked me any other questions yet, so I'm going to turn the slide, but this is what you should have. Check your window and make sure that you've got that pictured there. And then we'll go for part B. Does the graph have a vertical asymptote in this window? Yes. This one is dashed. You wouldn't see this on your calculator, but you can see it here, and it is 100. You can also look at the equation up here on the bottom. What value would make this 0 would be 100. So we do have a vertical asymptote at 100. And since it's vertical, it's x equals 100 is the vertical asymptote. That's how I would write that if I was doing my homework. Vertical asymptote is at x equals 100. For what values of P does this function serve as a model for the cost of removing particulate pollution? Well, if we're moving P, I believe was the, no, P is the percent. So probably only 0 to 100 makes sense. We're not going to have any negative values, which we get over on the left side of 0 and also over here. This thing down here doesn't really make sense. So probably 0 to 100 is what they're looking for. We can write that like interval notation from 0 to 100. You could also use inequalities. Use this information to determine, to better graph it. So change your window now. We don't want to look at this whole graph because we really just want to focus in on this part. So now change your window for x to go from 0 to 100 and y to go from 0 to 4,000. You should just get a better little picture that looks something like this. And then for part D, what does the part of the graph near the vertical asymptote tell us about the cost of removing pollution? So we're looking near the vertical asymptote. They're talking about, turn the slide here, right here. What's going on as we get closer and closer to this vertical asymptote? The cost is just shooting up really fast. So if we want to remove 100%, it's going to be pretty darn hard. So the higher, closer and closer to you get to removing 100% of the pollution, the higher that's going to cost you. That's all they want. Some kind of sentence like that. If you want to read what they said for the answer, that's part E right here. And we'll go on to the next part. So those were focusing on vertical asymptotes that go up and down. Now we're going to look at horizontal asymptotes. So not every graph has a horizontal asymptote, and not every graph, or sometimes the graph can cross a horizontal asymptote. It can't cross a vertical asymptote because when you plug in 0 on the bottom, you're going to get undefined. So there's not going to be an answer there. But horizontally, it can cross it and come back down to it. What they're talking about here is kind of looking at the end behavior. So if you have our very special 1 over x graph and you look like this, you kind of want to look at what the two ends are doing. So what is this left infinity side doing? It's getting closer and closer to 0 here. And on the right side, it's getting closer and closer to 0. So we have a horizontal asymptote right here at y equals 0. So horizontal asymptotes are going to be y equals, and vertical asymptotes are going to be x equals. So it's very important that you put that letter there. Don't just say the horizontal asymptote is 0. That doesn't work. You have to say y equals because we want the name of the line. All right, so to find the horizontal asymptote, there are 3 rules, and they're listed here, and I'm going to go through and explain them. And I'm going to put a simple little example for each one. So in math speak, we've got a polynomial on top and a polynomial on bottom. What we're going to want to look at is the degree of these polynomials. So how big is your x power, basically? So first of all, if the degree of the top is less than the bottom, so if there's like a higher power of x on the bottom, for example, x over x to the third plus 2, there's a quick little example. The bottom is bigger, then it's going to have a horizontal asymptote at 0. The way I remember this is if you plugged in numbers for x, like plug in a 1, plug in a 10, plug in 100, plug in 1,000, what's happening? The bottom is exploding and getting bigger and bigger and bigger, than way faster than the top is. So since the bottom is growing faster, if you think about a fraction, like 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, as the bottom gets bigger and bigger and bigger, that fraction is getting smaller and smaller and smaller and closer to 0. So I have a horizontal asymptote at y equals 0. That's when the bottom is bigger. So I'm going to skip down here. What if the top was bigger? What if I had x squared over x plus 2? The top is growing faster than the bottom. So that means it's growing, well, if the top is getting bigger and bigger, then my number is just getting bigger and bigger. So it's just going off to infinity. So there is no horizontal asymptote. And we'll talk about another type of asymptote in a minute, which will work on this kind of problem. But what you need to remember for now is if the bottom is bigger, it's getting closer to 0. If the top is bigger, it's going towards infinity. So there's no horizontal. The ends are going up or down. They're not flattening out. And then the last thing would be if they're both the same. So if I have like x squared plus 3 over 4x squared minus 5, something like that, where these both have the same degree on my x's, then what you do is you look at the coefficient of them. So the number that's in front of x squared on top would be a 1, and on bottom would be a 4th. So this would have a horizontal asymptote at y equals 1/4, because all this other stuff, when you get to huge numbers of x squared, plus 3 and minus 5 are not going to make a big difference. But the 1 and the 4, that's going to keep them in that proportion or ratio. So that's where your horizontal asymptote is going to be. So if they have the same degree, you just take these numbers that are in the front and make that your horizontal asymptote. So let's try that on some actual problems here. We have a cost function. This is actually average cost. So they took my cost equation and divided it by however many items there are, and that gives me average cost, which turns it into one of these rational functions. So this is the average daily cost in hundreds of dollars for the production of Stanley golf carts. X is the number of golf carts produced. So first of all, graph it. Again, remember to put parentheses when you go to type that in. So pause the video, plug that into Y1, and get a graph at this window that they provide here in part A. All right, so if you got that graphed, we have this picture here. Part B, does the graph in part A have a horizontal asymptote? If it has a horizontal asymptote, the ends will flatten out towards something. So the answer to that question is no. It does not have a horizontal asymptote. You can also tell, oh, my equation is right here, the degree of the top, the biggest one up here is x squared, the degree of the bottom. So the top is bigger than the bottom. So that follows the horizontal asymptote rule 3, which means it doesn't have one. So there is no horizontal asymptote. Part C, because this is a cost function and x can't be negative, where does this function actually make sense? Well, from 0 to 20 on the x-axis and 0 to 50 on the y-axis. So take a graph of that, and then we'll answer part D. Does the graph of the function using the window in A or B better model? Oh, I should say A or C. Is A or C better? Is this graph or this graph a better model? Well, it would be this one, because this is all positive and the number makes more sense for this data. And then part E, use technology to find the minimum daily average cost. Well, this is my average cost. So what I want to find is the minimum. So you have to use your calculator for this. You would have it graphed in here, and what we're looking for is the minimum. So use your calculator. Second, trace the minimum, do the left, the right, and you'll have it. The answer to that is at x equals 5. What does that mean in the context of this problem? When we make 5 golf carts, our average daily cost is $2,300 per cart, because the y value was in hundreds. All right, so what can happen if the degree of the top is bigger than the bottom is you can end up with a slant asymptote. And you can actually kind of see it in this picture right here. See this right here? The slant asymptote of this one is actually a horizontal, not a horizontal, it's a slanted line. So we're going to find out what that line is on this section. So how you do that? You divide them. That's it. You take the top divided by the bottom, and you look at just the rational function that's left over. The remainder really doesn't matter because that just kind of goes away. So that's pretty much it. Let's go ahead and try that out. So here is a problem. We're going to find the vertical, the horizontal, and the slant asymptotes. So let's start with vertical. Vertical asymptotes. Where do I find the vertical asymptotes? On the bottom, because I can't divide by 0. So you look at the bottom of the equation. What value would make this 0? You got it? The answer is x equals 2. Okay, horizontal asymptotes. Horizontal asymptotes come from comparing them. So if I compare the degree of the top to the degree of the bottom, the top is bigger than the bottom, so there isn't one. And then the slant asymptote, that's what we're going to do right now. So to find the slant asymptotes, the trick is divide. So I need to divide the top by the bottom. But remember, when you do long division, you have to fill in 0 placeholders if it's missing a term. So we're missing the x term, so I had to put a 0 there. Now we're going to do long division. These shouldn't be too complicated. Like when we did our assignments back in the fall, they were a lot longer. This one's not so bad. So x into x squared is x. X times x is x squared. I have to distribute this. And x times -2 is minus 2x. Now remember, this is the hard part. We have to subtract both of these terms. So we're going to add the opposite. So now when I subtract, these cancel out and I get positive 2x. So that's the first step of the division. Then we bring down the +4 and we go again. So x into 2x? 2x divided by x is 2. So I need a +2 here. Then when I multiply this, I get 2x minus 4. And then when I subtract, very carefully, a line, change both signs. These will cross out and you get a remainder of 8. But the good news is the remainder doesn't matter. So as long as you don't make any mistakes until the last step, you're fine. This guy up here is your slant asymptote. This slant asymptote is at y equals x plus 2. So if you graph the line y equals x plus 2, that's what your graph is going to follow. So if you put this in your calculator, you'll see that. But I think I've got a picture over here for you. I'm just going to, these are the solutions from the computer. If you want to read them, you can pause this and see what they did. But the answers are right here. So we've got a vertical asymptote at x equals 2 and a slant asymptote at y equals x plus 2. And that concludes video 1. Come back for video 2 on how to solve rational expressions.